Good afternoon and welcome to the project update video for the Automated Strain Analysis and Mapping Using TEM Diffraction Data project. My name is Aaron Barbosa and I am an undergraduate student here at Texas A&M University in the Computer Engineering program. This project is sponsored by the online OREU program at Texas A&M University, and the mentors heading this project are Dr. Kelvin Xie and graduate student Dashin Zhao. This project is also being worked on with Aniket Patel, Antonio Sanchez, and Jihad Sino. So what is TEM? TEM stands for Transmission Electron Microscope, and the purpose of the TEM diffraction data is to analyze and identify crystalline structures in different materials and to analyze the crystal defects present in those materials. As you can see, this is a diagram of the electron microscope and how the data is acquired. So you take a very thin sample, usually 100 nanometers, and you place it right here in this diagram, as you can see, and it is shot with a beam of high energy electrons, and the resulting image is generated, as you can see here. Our goals going into this project. Going into this project, we wanted to improve upon what was already available for TEM diffraction data analysis, as the commercial software available is limited in the types of data it can analyze and the speed at which it processes this data. Our initial main goal was to create a more available and user-friendly program that encompasses multiple functions commonly needed for strain stress analysis. We also wanted to hopefully improve upon the commercially available software and to make a more open source version that everyone can edit and improve with time. Our main goal was to create a more informational software, as the current software functions like a black box where you can input data and the program creates an output, but it does not give you any context as to how it arrived at that answer. Our methods for doing this. This is all being done in the Python coding language due to the availability and flexibility of its user-created packages. We are currently using Jupyter Lab/Notebook for our coding IDE, and in order to achieve timely results, we have been utilizing the Texas A&M supercomputer due to the large files being used in this project. Our program so far. Our program takes the large .blo file shown on the far left, right here, and takes the embedded image of the diffraction pattern shown in the middle, right here, from each of the pixels in this image, and performs some image manipulations and disk templating to enable the computer to accurately plot and index the center spots of each bright spot. As you can see here, this is what our program sees, essentially. This method can remove some of the spots seen in the original image, but only the main spots are needed for the analysis we are doing. So as you can see right here and here is basically almost every spot in between is basically completely lost, but we only really need the center spot and one of these spots to be consistent across the entire .blo file, and that's all we need, so that's what we're going to be working with for our program. This slide shows a screenshot of the commercially available software for strain analysis and the output of the software for the file we are using right now. We originally wanted to be as close as we could to the screenshot so that we could be more confident in our program's accuracy. As you can see, we are using this spot right here that is circled in blue, and this is the spot that was used to generate these results in the commercial software. On this slide, we have our output from the program we created. As you can see, it matches up decently well to the commercial software's output. Many of the dislocations that can be seen in our output match some of the ones seen in the commercial software. So these ones right here, and this one right here, you can see it matches up with this main one here, and this main one here, and this main one here. There is quite a bit more noise in our image, which is basically just due to how we're indexing our bright spots, which can be fixed, so we are currently working on fixing that right now. There is still some improvements to accuracy that we need to make, but this is a promising result for a first file. As you can see here, this is another file we were given. We only have two right now, but this is the diffraction patterns present in this overall image. We chose this one circled here, this 4 o'clock spot, and this is the generated strain heat map of this image. We have presented this to the professor, and it seems that this is inconsistent with what the commercial software is reporting, so we are still in the process of figuring out just what exactly is going on with this image being generated. While working on the main function in our program, the stress strain analysis function, our mentor decided it would be a good idea to invest in including a virtual dark field image function in our program. This will aid in our material analysis capabilities of our software and reduce the number of softwares you need to have installed in order to create these types of images. A virtual dark field image is light intensity taken from one spot of the diffraction pattern for the entire file to produce a heat map that highlights dislocations in the material very well. We wanted to include this function in our program because it seemed very important for general material science analysis. Our virtual dark field function works very well, as you can see from the images shown. The image to the far left is the original image generated from the commercial software, and our results are the 3 images to the right of that image. As you can see, our results line up almost identically to the commercial image, depending on which spot in the diffraction pattern you choose. So this one is taken from the spot 7371, and this is the image that was generated. This is essentially the center spot that was generated. This is a random point that we took, 6797, and as you can see, it very closely resembles the output of the commercial software. And this point 00 was just a test in the darkest part of the diffraction pattern right here, if it could pick out any dislocations present, and it actually could. After creating all these functions, we moved on to the graphics user interface. We originally started with a simple command line menu that took numbers as inputs, as you can see here. That is this image right here. We then moved on to a more basic looking graphics user interface right here in the middle. And then we finally arrived at this version right here. We have a GUI we are satisfied with for now, but we will most likely edit this further to add more functions and improve the look of the program. Our mentor recommended adding a A&M logo in the corner, so that's something we'll be working on. Originally, our program was extremely unoptimized and relied on brute force to complete one image. Our main goal was to optimize and reduce the computing times. Our program took 36 minutes on the A&M supercomputer originally, but thanks to some optimizations using multiprocessing packages in Python, we were able to drastically decrease the amount of time needed to generate our program's results. As you can see, one virtual bright field image or dark field image took 36 minutes to generate, and with our new method for processing, it took only 80 seconds to generate this image, which is an amazing improvement. Some future improvements that have already been planned out are adding mouse support for selecting which spot to use for either the virtual dark field generation or the strain stress analysis. Some future graphics user interface adjustments, such as improving clarity and adding more functions. Testing with further new files and materials to make sure that our program is accurate and precise. And just general bug fixes with our program's indexing and making sure that the performance is up to our standard. Overall, our program is in a good state to start testing and adjusting. The overall speed has been optimized and the graphics user interface is in an acceptable working state. Our next goal going forward is to test more files and compare the commercial software to see where any inconsistencies may lie. Unfortunately, creating this program took a large amount of time, so any concrete findings that we would have would take a bit more time to gather after we test our program's functionality with new materials that the commercial software struggled with. Even though we don't have any concrete findings yet, hopefully in the future our program can be used at the very least as a second source or double check for these images being generated so that there is something to compare to the commercial software that's available. Even though the OREU program is coming to a close in a few days, we still plan to continue this project into the semester and hopefully end it strong with some new findings. This has been the Automated Strain Analysis and Mapping Using TEM Diffraction Data Project update video. I'm Aaron Barbosa. Thank you for watching and have a great day.